You're listening to the Brain Man's podcast.
It is impossible for a man to learn what he thinks he already knows, Epictetus. And there is a lot to know about noses. Why can we smell Kastuba from a mile away? How do noses work? These are the questions that have plagued our generation for millennia. For such a large part of our face, it's surprising that science hasn't come up with an explanation for how it works. So take a seat and smell the roses, because I'm your host Silas.
And I'm Kastuba.
And we are going to explore the quantum schnoz on the Brain Man's podcast.
Scientists have been able to link our ability to smell to a collection of cells that line our nasal passageways. These cells are called olfactory receptors and have been common knowledge for quite some time. Despite this, we've never been able to take a close look at them to see how the science behind them works.
Well, what are we waiting for? We should just take the olfactory receptors out of the nose. Wouldn't that make it really easy to see under a microscope?
Unfortunately, science is never that simple. These receptors lose their shape and become inert outside the body, much like a blobfish, which loses its shape when taken out of the high pressures of its natural environment. In other words, we never had the opportunity to study the olfactory in action.
And because we don't know much about how it works, we can only really go off an educated guess. I guess that's the reason why there are so many theories on smell.
You're right. Let's go over some of the prevailing theories and see where they fit into the grand scheme of things. If you recall, I said that scientists knew about olfactory receptors for a while. They also knew that molecules had to interact with these receptors in some way and send a nervous signal. This brings us to the first two theories, the shape model and the vibration model. Firstly, let's talk about the shape model of smell. It proposes that olfactory receptors have specific shapes that bind to the shape of an odor molecule, producing a specific neural impulse. The best way to visualize this is like a lock and key, where different combinations of bound molecules create the perception of a specific smell.
Now wait a second, Kastuba. There's over 10,000 specific odor molecules that humans can detect, and only 400 types of receptors that are available to bind to. Clearly, there's something missing from this theory.
The weak shape model can explain this discrepancy. In this model, receptors only bind to specific functional groups on a molecule, meaning that completely different molecules can possess the same smells, because they have the same key, if you will. The massive caveat to this shape-based model is that molecules with completely different structures smell similar to each other, and molecules with the same functional groups end up smelling completely different from each other.
Wow, yet again we have another failed attempt at an explanation for this phenomenon. Hey, you know what I just read about? The vibrational theory. This is built on the notion that receptors can detect the vibrational frequency of specific odor molecules.
Oh yeah, I heard about that. This theory caused quite a stir in the scientific schnoz community. So much so that it caused perfume expert turned scientist Luca Chirin to go out and test the theory for himself. He used a sulfur compound as a baseline and selected a completely unrelated molecule that happened to have the same vibrational frequency. The results spoke for themselves when they both reeked of rotten eggs. However...
Let me guess, is there another issue with this theory of smell?
Right you are. Even though the vibration model covers most gaps in our understanding of smell, it is still unclear how the nose is actually able to measure these vibrational frequencies.
Does it have anything to do with our topic, the quantum schnoz?
Right you are. This is where the quantum tunneling theory comes into play, and it's the most comprehensive theory we have on smell. On the quantum scale of matter, particles such as electrons experience counterintuitive properties. Electrons, in our case, are able to pass through barriers that they would not have enough energy to overcome in a classical sense. Quantum tunneling is a consequence to the probabilistic wave nature of quantum particles. Lighter particles and smaller barriers increase the probability of this event occurring. Well, first of all, we need to focus on a subset of quantum tunneling called inelastic electron tunneling. And before we do that, we need to look at elastic electron tunneling. Let's visualize it like this. There's two pieces of a conductor, separated by a very small gap. On this scale, the electron should be able to tunnel if energy such as electrical energy is applied. This electron has its own energy to account for too, and the conductive material on the other side needs to have a hole that has the same energy for the electron to tunnel through. This is called elastic electron tunneling.
Whoa. That was a whole lot of mumbo-jumbo, Tuba. Now we can describe what we are really interested in. Inelastic electron tunneling. In this case, the same conditions apply, however, the deficit in the opposite conductor is smaller. The electron won't tunnel to the conductor in this condition because it has too much energy. This behavior changes when a molecule is put between the two conductors, though. If the difference between the electron's energy and the hole matches with the energy required to resonate the molecule, the electron tunnels through and imparts its spare energy to vibrate the molecule. Because of this property of inelastic electron tunneling, we can tell the vibrational frequency of certain molecules. The quantum model of smell believes these processes are occurring in the olfactory sensors to produce the perception of smells.
That sounds rather far-fetched, though.
May seem like a stretch, but it is the most plausible explanation that accounts for all the issues that have more or less disproven the other models. Our nervous system already uses electrochemical gradients to send signals across our bodies, so humans are rather accustomed to making electrons do their bidding, adding further credibility to this model. Experiments have shown that test subjects are able to smell the difference between regular hydrogen and its heavier isotope deuterium. These diatomic molecules have the same chemical properties and shape, but vibrate at different frequencies. The crazy part is that this evidence was consistent across fruit flies and even white fish.
While the quantum model does fit in with what we know about smell, it does have one oversight, the chirality of molecules. Essentially, molecules can come in two forms, right-handed and left-handed. These forms are like mirror images of each other. Any amount of translation or rotation will never be able to make them look alike. Chiral pairs are made up of the same atoms and bonds though, so they have the same vibrational frequency. Despite this, different chiral counterparts do smell different from each other.
Well, if that's the case, then we shouldn't be too hasty in throwing out the weak shape model. I mean, there must be some shape criteria being fulfilled before inelastic electron tunneling can happen. Otherwise, how would we smell which chiral counterpart is which?
Okay, well, maybe it's a combination of these theories. Tying out everything we know about, paint the most likely scenario for the viewers at home. An odor molecule enters the olfactory receptor and binds to a specific type of receptor in accordance to the weak shape model. Next, an electron held in one conductive end of the receptor checks for resonance through inelastic tunneling. The end product of all these complicated systems working together is a perception of smell. Despite all of these theories, seeing is believing though, and we need to find a way to look at the receptors in order to truly know.
Wow. And being able to smell isn't the only example of how quantum tunneling affects our daily lives. It's also used in the sun. In order for the sun to keep shining, protons need to fuse together and release energy. However, due to Coulomb forces, protons don't really want to fuse together. We can overcome these forces of repulsion and bring them close enough together to fuse, with enough external energy, such as heat. However, in the sun's case, this would require a temperature of approximately 100 million degrees Celsius, which the sun does not reach.
So, how exactly does fusion happen?
Only God knows, Kastuba. Just kidding, it uses quantum tunneling. Since protons are just waves of probability, in the sun there is a 1 in 10 to the 28th chance that a proton is able to quantum tunnel through and fuse with other protons to release energy and kickstart the cycle of fusion. Wouldn't that be crazy? Something in the core of the sun happening in our nostrils?
When you think of the word quantum mechanics, images of supercomputers and particle accelerators come to mind. However, these examples show that quantum mechanics are responsible for life as we know it. The world of quantum mechanics is everywhere.
Even right under our noses.
Silencing Kastuba on the track.
Work on this podcast. Ranging the forecast. Get me out of this class. Does Mr. Jess like the rat? Hope he doesn't lambaste. Physics. Bad. Podcast. Big sad. Jackson. Big rat. Rayman's big mad.